Welcome to section 4.3, separable differential equations. So, separable differential equations have the form dy over dx equals g of x over h of y. And what separable means is that you can separate the differentials. You can separate the dy's and the dx's. I'm going to use a different color for the dx. And then after you separate them, you can integrate both sides with respect to their variables. Here you have h of y dy, g of x dx. And what integrating does is it gives you back the original function, right? But when you integrate, if it's an indefinite integral, you have to remember to write your plus c's. So we can see here, after we integrate, we end up getting this plus c1 on the left and c2 on the right. So if we're trying to solve for h of y, we have h of y equals g of x plus c2 minus c1. C is just a constant. And what this means is we can now redefine c to be c2 minus c1, because c1 is a constant, c2 is a constant, and c2 minus c1 is also, you guessed it, a constant. So after redefining that c equals c2 minus c1, we can just write that h of y equals g of x plus c. We do not need to use two constants. So let's look at some examples. Example 1 wants us to solve dy over dx equals sine x. So first things first, I would move the dx over to the other side to join its sine x buddy. Next, I would integrate both sides. And on the left side, we would just get y. And I'll do it with c1 and c2 just for this problem so you can see what that would look like. But for future reference, you do not need to show that. So y plus c1, your first constant, equals cosine or negative cosine x plus c2. Now, if you want to isolate y, you would redefine c to equal c2 minus c1 because we want to move this guy to the other side. We want y by its lonesome, right? So we would get that y equals negative cosine x plus c. Now looking at example 2. Solve the differential equation dy over dx equals 1 plus e to the 2x. This one's a little bit spicier, but it's not too bad. So, again, move the dx to the other side. Remember your parentheses. It's very important to include parentheses for this whole thing, because this dx goes to everybody. Second, integrate both sides. And you get that y equals, now we don't need to keep showing the c1 and c2 because of what we said above. Y equals integral of 1 is just x. And integral of e to the 2x is 1/2 e to the 2x plus c. That's not too bad. So now, for example 3, we will get both an implicit and explicit answer. First, we will move that y dx over to the other side. Next, we will group up the dy with the y and the dx with the 1 plus x. So we get that 1 over y dy equals 1 over 1 plus x dx, like so. Just go over with the highlighter. There we go. Now, it's time for us to integrate. After integrating, we get that ln of y equals ln of 1 plus x plus c. And this guy becomes our implicit answer. We want y to be all by itself to be an explicit answer. So without further ado, let's see how we can get that explicit answer. I'm just going to rewrite our implicit really quick, and I'll show you why in a second. It's because I want to do something to get rid of these pesky ln's. And the first thing that comes to my mind is base e, because if you do e to the ln of y, you see what happens is that this cancels out, and on the left side, we're just left with y all by its lonesome. But on the right side, here, first let's rewrite this, e to the ln of 1 plus x plus c. Now, if you recall your exponent rules, when you have something like a to the m plus n, you can break that down into a to the m times a to the n. And this is your exponent rules, exponent product rules. Now, let me just make this smaller so that we'll have some space. There. So, same rule applies. Y equals, we're going to break this down, e to the ln of 1 plus x times, recall back to the exponent rules, we'll have e is a number to a constant is just gonna be, another constant. So you can really just call this c. Y equals, this goes away, 1 plus x, and we're gonna call this c. And this is our explicit answer. Okay, so now moving on to example 4, looks like we have an initial condition. What this means is they will want a particular solution. They want not for a general solution in which our answer includes a c. They want us to find what that c is. So dy dx equals negative x over y. I am going to cross multiply, so I'm just gonna cross, and I'll get that y dy equals negative x dx. Integrate both sides, and we get that 1/2 y squared equals negative 1/2 x squared. I'm just going to get rid of the 1/2 since they are on both sides, and I'm left with y squared equals negative x squared plus c. Now, y squared plus x squared equals c is our general solution. General. Because we haven't solved for what c is, and that's why we need to use our initial condition that we are given. Now, just a quick note, what does this equation represent? Y squared plus x squared equals c. Or think of it as x squared plus y squared equals c. This is an equation of a circle. Circle with radius square root of c. Because this is your equation of a circle. Is x squared plus y squared equals r squared. And this circle is centered at, very good, 0, 0, centered at the origin. But now, since it gave us an initial condition, it wants us to find the particular solution. Wants us to solve for the c. We can do that, that's not bad. We're given that we have this point, x equals 4, y equals 3. If we just plug that in, and I'm going to rewrite this as x squared plus y squared equals c, because I just got this from down here. Plug in your x, plug in your y, and just solve. Very easy. So I get 4 squared plus 3 squared equals c. 16 plus 9, I hope you can do that in your head, is 25. So x squared plus y squared equals 25 is our particular solution. And that's it. Particular. And this is circle with radius 5. Yay! Okay. Moving on. First things first, I want to move that y dy over onto the other side. So x e to the negative y sine x dx equals y dy. Now, I have a feeling that we should divide by e to the negative y. Just to get it all with the y's. And this cancels out on the left side. So x sine x dx equals, now if you have 1 over e to the negative y, this is the same thing as e to the y. So on the right side you'll have y e to the y dy. Now it's time to integrate both sides. And what integration technique should we use here? Notice that we have a polynomial times a trig function, and we have a polynomial times an exponential. Hint, hint, it starts with the t. Tabular method. We will do tabular on the left and on the right. So first, let's do tabular for x sine x dx. Remember, for tabular, we make this little table where on one side you'll have diff for differentiate, and on the other you'll have int for integrate. Always differentiate the polynomial. So if you have x, differentiate. Very simple, very straightforward. Now, if you have sine x and we want to integrate, first is negative cosine x on the first integration. Now we integrate it again when we get negative sine x. Now, remember the signs alternate for tabular, so you will have plus, minus, and you will multiply. Be very, very careful with the signs, okay? It is very easy to get messed up. Here we have x times negative cosine x, x times negative cosine x, bring the negative out in the front, And a negative times a negative is a positive. You have plus sine x plus c. And now we're done with the left side, but we still have to do it again for the right side. So you have y, 1, 0, differentiate, and for e to the y, oh, look at that. It's so beautiful. And just a quick note about the plus c, doesn't really matter what side you put it on as long as you write it. And I'm just going to rewrite this with the sine x in front. That's sine x minus x cosine x plus c. Very, very nice. This is our implicit answer. Y e to the y minus e to the y. And copy. This is our implicit answer. But in this case, the explicit answer cannot be rendered. So we can't find an explicit answer for this one as we did for our previous example, which was example 3. Note how for this one we were able to get y all by its lonesome. For example 5, we only have an implicit answer. That's as good as it gets, guys. Highlight. Now we're on to our last example of the section. We're going to be looking at a basic application of what we have learned today about separable differential equations with Newton's law of cooling. Now, as you can see on the right, we have an equation. We have a differential equation with dt, capital T over dt, representing the rate of change of the temperature, rate of change of temperature with respect to time. So capital T stands for temperature, while lowercase t represents time. And on the right side of the equation, we've got a couple of things. We've got our K. This is our proportionality constant. We've got our T. This is the temperature of the object at any time T, lowercase t. So temp of object at any time T. And lastly, we have T sub S, which is the surrounding temperature. For instance, the temperature of the room. Now that we've looked at Newton's law of cooling's formula and broken it down, let's do example 6. Get out your calculators as well, because in part 3 and 4 we will be needing to do some computations. This question says, a hard-boiled egg at 98 degrees Celsius is put into a sink of 18 degrees Celsius water. After 5 minutes, the egg's temperature is 38 degrees Celsius. If the water has not warmed appreciably, how long will it take the egg to reach 20 degrees Celsius? Okay, part 1 tells us to use the technique of separable differential equations to render a working model for this example. It wants us to find capital T of T, and this represents the temperature at any given time T. So the first step into doing this is I want to get this guy over to the other side to be with the dt. And I want to move the lowercase dt over to the right. So let's go ahead and do that. The next step, I will integrate both sides. Business as usual. Oops, I already wrote dt. Evaluate the integral. Now, recall what we did as well in a previous example, is we used base e to get rid of the ln's. And this is the same as e to the negative k times t times e to the c. There we go. Perfect. This cancels out, and we're left with t minus 18 equals... Now, I'm just going to call this guy C1 because E is a number. It's roughly 2.718, blah, 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 on and on. So a number to a constant ends up being, that's right, a constant. So we're just going to call it C1. And we get t minus 18 equals C1 times e to the kt, negative kt. Step 6, we just want to move that pesky 18 to the other side so we can get t all by itself. All by myself. And there we go. We have the original function. Hey, I didn't want an oval. I wanted a rectangle. That's better. Okay, moving on to part 2. Determine the value of the coefficient, and in this case, when it says coefficient, we are referring to C1 coefficient using the initial data. Okay, to find C1, let's first write down our function, and I'm going to leave t blank for a reason. Now it says using the initial data. So that means the initial time, lowercase t, should equal 0, right? When you're just putting it down into the sink. So if t equals 0, 0 goes over here and 0 goes here. So that means e to the something times 0 is going to just be 1, right? Because e to the 0 equals 1. So this guy is 1. And t initial equals 18 plus C1. I have a feeling that we know what t initial is, because if we look back at the problem, hey, it tells us what t initial is. 98 degrees Celsius. So 98 equals 18 plus, use a different color here, 18 plus C1. And we get that C1 equals 80. And this means that our function is 18 plus, we said C1 is 80. So 18 plus 80, e to the negative kt. So after plugging C1 back into the function, this is what we get. We're all done with part 2 now. Part 3 wants us to determine the value of the proportionality constant k using the secondary data. So let's reference back to our function, again, leaving the time blank, TBD. Well, we already know that we can't use t equals 0 because of what we saw over here. E to the negative k times 0 is just 1. This is not helpful for finding our k. Angry face. What we need is a different number, a number in which the time is not 0. Are we given that? Yes, we are. Because it says after 5 minutes up here. After 5 minutes. So we know that we can use t equals 5. And are we given what the temperature after 5 minutes is? Yes, we are. 38 degrees Celsius. Perfecto. Now I'm just going to move the 18 over to the other side. So I'm left with 20 equals 80 e to the negative 5k. I am going to divide by 80 on both sides. So this reduces to 1/4. I get 1/4 equals e to the negative 5k. And taking the ln of both sides, we get negative 5k equals ln of 1/4. And k equals ln of 1/4 divided by negative 5. If you punch that into your calculator, you'll get approximately 0.2773. This is our proportionality constant, K. Now part 4, actually answering the question. How long will it take the egg to reach 20 degrees Celsius? Well, 20 degrees Celsius, this represents the temperature at time t, and it wants us to find the time t. This is what it wants us to solve for. Solve for time t. And we know everything to solve for it. We know that the temperature is 20 degrees. We know C1. We know K, and I'm going to use the exact form for K. I'm not going to use the rounded version just because I want a precise answer. And this is to the power of, so I'm going to make it look like that. Nice. Oops. Now if we move the 18 over, you get 20 minus 18 equals 2. Divide both sides by 80. 2 over 80 is the same as 1 over 40. And that equals, I am lazy and I'm just going to copy this. Much better, much better. Take the ln of both sides. And we're almost there. We just need to isolate t now. So t equals ln of 1 over 40 times negative 5, because when you're dividing, you're multiplying by the reciprocal, over ln of 4. And that equals 5 ln of 40 over ln of 4. Now, if you're wondering how I got 5 ln of 40 from negative 5 ln 1 over 40, it's because I just brought the negative inside, so the 1 over 40 became 1 over 40 reciprocal, and that is ln of 40. And if you punch this into your calculator, you should get approximately 13.3 minutes. But it does say answer to the nearest minute, so we're going to round this to 13 minutes. Phew, what a problem. We're finally done. We did a lot today. We looked at separables and we also looked at an application. So great job. You made it to the end.